standard component that you'd put in, for instance, the traditional larger components. And just as further validation, a MEPTEC report that came out last year highlighted a few areas where, metrology of MEMS devices remains important, remains a barrier. So with MEMS development, there's large numbers of process iterations. Those can take weeks or months. Surface conditions are usually affected by the processing steps, and the device's 3D geometry actually has a significant effect on development problems with the MEMS devices, particularly contamination. And all of those really create a high demand for metrology in MEMS. And just to look at some of the MEMS failure modes, this is a bit of an eye chart, but you can see that each of the different primary MEMS devices have significant numbers of different failure modes that need to be tested and verified to ensure proper device performance. So you have everything from contamination to environmental creep, leakages, strange deformations that can happen, outgassing that can affect performance, effects of temperature and electrical shorts. So comprehensive metrology does play a key role over the entire MEMS production cycle. So during R&D, you want to measure the real device behavior without effects from packaging typically. During pre-production, rapid, accurate metrology can shorten your feedback loops and make sure your devices are rapidly iterating towards the final design. And then during production, MEMS actually undergo a very high test rate to maintain adequate process control, to provide further cost reduction as you're feeding problems back into the production cycle, and then also for failure analysis to ensure that any ongoing problems are rapidly caught and the root cause failure discovered. And then in post-production, there's a lot of longevity and cycle testing of MEMS. There's lots of tests that go on relative to endurance and environmental analysis. And then MEMS are always being enhanced. And, just the picture on the right comes from TI, and it's a representative, cartoon of the micromirror arrays used in most projectors. And you can see, just the complexity of the devices. There's literally, 10 layers and probably, 15 critical components per mirror, all of which that need to interact properly for proper device performance. So people will characterize feature heights, lateral dimensions, line width, angles, radii of curvature. They'll look at stress. Roughness is very critical, both in MEMS that are doing optical things, such as the micromirror arrays. In biological samples, it can affect adherence and acceptance by the body. And it can also lead to defects and other problems. And then defects and contamination need to be characterized as well to ensure that the devices are going to perform properly. Then different MEMS metrology techniques really have different strengths. And there's not one technique that can do absolutely everything. So I thought this chart was useful because it kind of highlights the four main areas that are used for MEMS tests. So the first are 3D microscopes or optical interferometers. The second category are stylus profilers, which are really the workhorses of any metrology lab. It's usually the first characterization any metrology lab gets, and the one that's kind of most readily used by a wide variety of people. Atomic force microscopes and scanning electron microscopes. So in terms of quantification, the SEM probably provides the least quantification, but I'd say you're going to see the most SEM pictures in literature because it provides a very nice picture that kind of people intuitively understand. Optical interferometry, 3D microscopes provide non-contact, non-destructive methods. Stylus, they'll contact, but you can get very low force so as not to damage the devices. AFM is really, you can argue whether it's really contact or not, but it's a non-destructive technique. SEMs are often non-contact, but there can be problems due to charging, and then sometimes you have to cross-section. And so it can be a destructive test. In terms of acquisition speed, 3D microscopes are going to be the fastest. SEMs and AFMs are going to be the slowest, typically. And in terms of time to result, an SEM typically requires the most time to result because of vacuum, cross-sectioning, and general system usage. Vertical measurement range, there's a wide variety here, anything from up to 10 millimeters on the optical side down to 20 microns on the atomic force microscope side. Vertical resolution, almost all of these will have acceptable vertical resolution on the order of an angstrom or a few nanometers, so that's generally not a concern. Lateral resolution, most MEMS devices are in the micron, few micron size range, all the way up to millimeters. And so most of these techniques are acceptable. There are some devices where stylus techniques may not be ideal, but any of these techniques generally provide the lateral resolution. If you need to look at sidewalls or undercut, you're going to need an AFM or an SEM to do that. And if you want to look at packaged devices, so if you want to look at something for which there is no physical access, your only choice essentially are the optical techniques. And last, the only technique that really is capable of doing dynamic measurements is a 3D microscope. And we'll get into how that's accomplished later. In terms of price point, there's almost a price that suits any needs. Most of these technologies are fairly mature, and so you get a fairly broad range of pricing depending on your needs. So the remainder of the talk is going to really concentrate on 3D microscopes, because we've seen over the years that of the various technologies we're aware of and that we offer, in the MEMS field in particular, 3D microscopes are really the most widely adopted measurement solution. And they're very simple devices in principle. They're just modified bright field microscopes where you add a precision scanner and a specialized objective. And when you do those two things, you're able to get a signal back that allows you to do three-dimensional capability. And really, in terms of the specialized objective, what we're doing is we put a beam splitter in the objective, which is the bottom blue bar you see. And that splits the light, and part of it goes to your sample, part of it goes to a very small reference mirror that's of high quality. Light bounces off both the sample and the reference mirror and gets recombined. And we can look at that recombined light and essentially compare the sample to our reference and get three-dimensional height. It's a fairly simple technique, a very powerful technique. What does that look like in practice? This is about a 3x slowed down measurement where you scan the microscope objective through focus, and you see those bright and dark bands. On the right here, we actually are looking at a step height. And when those bands go by, we track the position of those bands versus the height of the objective that we're scanning through focus, and that allows us to get a three-dimensional map. So one of the advantages of interferometry for MEMS devices is there's no loss in vertical resolution no matter what your field of view is. Again, this is a microscope, and so I can pick an objective that's a 1x objective with a 15 millimeter field of view, or I can pick a 115x objective with a 10 micron field of view, and almost anything in between. And as you scale your lateral resolution and your lateral field of view, you get no loss in the sub-nanometer vertical capabilities. And so even on a device like this microgear, you can see print through from the manufacturing process, from the lithographic process. Very fine details can be imaged even over large fields of view. It's a mature technology, and so 3D microscopes actually offer very advanced feature finding software, so they can take an image, they can segment it, and report statistics on each segment of the image. So in this particular case where we're looking at a micromirror array, we can look at tilt, roughness, curvature, we can look at relative heights between the regions, and you can actually look up to thousands of regions within a single measurement and characterize those. And you can also report steps, angles, and roughness for each region independent of the others, and then aggregated together as well. A lot of MEMS, particularly in development,